we are here at Analytical Answers, a company which has been performing materials and failure analysis for more than 25 years. Over that time, they've completed over 50,000 analyses, a high percentage of which deal with structural characterization, cross-sectioning, and thin films. We will discuss our newest capability today, Transmission Electron Microscopy, which allows us to take these analyses further into the nanoscale. We're going to discuss TEM today with Bill Harris, a senior scientist here at Analytical Answers. He has been working in materials characterization for more than 20 years and would like to show you our new capabilities. Before we do that, we want to give a brief shout out and congratulations to Mr. Frank Gorman. Frank, and you're going to hear a little bit more about him at the end of the webinar, but we want to congratulate him because he submitted the winning idea for the December 5th webinar. That idea is analytical solutions to your engineering and manufacturing problems. Which tool works best to solve which problem? And you'll hear more about the December 5th webinar, as well as our upcoming November webinar at the end of Bill's session. But we wanted to give a shout out to Frank, who is in the audience today, and thank him for his wonderful idea. So with that, I'd like to hand it over to Bill Harris, PhD, who's going to be sharing more information with you about transmission electron microscopy and scanning TEM, and how it can characterize defects, ultrastructures, and composition. Take it away, Bill.
Okay, thank you very much, Christina. Well, welcome to today's webinar. I'm going to spend the next few minutes, as Christina said, giving you an introduction to transmission electron microscopy and scanning transmission electron microscopy. Just a quick overview of what I'll be presenting today then. I'm just going to briefly review electron microscopy in general and use that as the basis to point out some of the advantages of moving to a transmission setup. I'll then move into transmission electron microscopy per se and try to give a variety of examples that show the power of this technique, and then follow up with a brief summary. So, all the techniques I've mentioned so far do use electrons, and why do we want to do that? Well, we have high brightness sources that are readily available. We can produce a very finely focused monochromatic incident beam. We can use charged particle optics to manipulate these beams, both in focusing them and moving them across the surface using either electromagnetic or electrostatic lenses and deflectors. But importantly, electrons interact strongly with the material upon impact, and they result in a variety of emitted species that we can then use for various analytical schemes. I've tried to show that schematically here at the right-hand side of the slide. We have our incident beam striking the sample surface, and we generate a variety of species then. The secondary electrons are what we use to form our normal scanning electron image. We just collect those in an imaging detector. We step the incident beam across the surface in a point-by-point fashion while we detect those, and in that way we form a raster scanned image of the sample. Backscattered electrons are also emitted. We use those in imaging studies because they have the advantage of producing some mass-dependent contrast. Elements and materials in the sample that are heavier provide a larger yield of backscattered electrons and therefore appear brighter in the resultant image. And also, as the electrons are interacting with the atoms in the sample, they will cause generation of characteristic X-ray emission. And using a X-ray spectrometer then, we can detect those, separate them by energy, and assign the specific X-ray lines to the elements present in the sample, and in that way get a elemental composition. So for all those reasons, scanning electron microscopy, or SEM, has really over the years developed into a workhorse tool for high magnification imaging. And again, I just give a little schematic here of a SEM instrument where our electron beam is focused and scanned across our sample. Our detector here sitting above the sample detects secondary electrons or backscattered electrons, what have you, and would then form this image in a raster scan mechanism. And as I mentioned, we can also do compositional analysis using energy dispersive X-ray spectroscopy, or EDS. Well, as powerful as it is, there are some limitations in the SEM. Well, it's capable of very good resolution, down to about 1 nanometer spatial resolution. Some problems in materials require even higher resolving power. We like to see even finer structure and resolve those. Also, the interaction of the electron with the sample causes some beam spread upon entering the sample, and that will degrade our resolution in some imaging modes. And particularly if we're doing EDS compositional analysis. Again, on this quick schematic at the right, our probe beam is impacting on the sample surface. Secondary electrons that are used in the image are emitted very much along the same lines as the incident probe size. But if we go to backscattered electrons, we start to get into this teardrop-shaped region of excitation, and they're coming from deeper within the sample, and therefore showing some effects of this spread. Where we really see this is if we're doing X-ray microanalysis, because this entire volume that the electron has penetrated usually has enough energy to generate characteristic X-rays. So you can see that our fine focus point probe that may be a couple of nanometers in size balloons out to about a micron or more, depending on the material. Well, what can we do about that? We can move to a scanning transmission electron analysis in the SEM. We can do that by taking our bulk sample and actually removing most of the material from the back side, leaving us with this very fine sliver of material to perform our analysis on. And what that does, by removing the backside of the material, you take out all this extra material that causes scattering within and also X-ray generation from within this volume, and confine it to very much near the entry point of the electron probe. Now, the thickness that's required for this is on the order of 100 nanometers or less, so we do need to make very thin samples to reach electron transparency and have this kick in for us. And how do we do that? Well, here we use a focused ion beam sample prep method, or FIB. A focused ion beam instrument is completely analogous to a SEM, but rather than using an electron beam as our image generation beam, we use a energetic ion beam, in this case a gallium ion beam. Interaction of that beam with the sample surface will also create secondary electrons, and we can form a raster scan image in the FIB completely analogous to what we do in the SEM by scanning that beam across the sample surface and doing a point-by-point secondary electron detection. We can also increase the current density in the FIB and begin to actually sputter and remove material from the sample, and that's what I've shown here. We've cut a wedge-shaped crater into the surface of this sample of interest to expose this cross-sectional face, which you can see has several layers. And we would then take this into our scanning electron microscope for higher resolution imaging. You can also see in this image this mesa that's on top of the sample surface. That's a platinum strap that we've actually deposited in the FIB instrument using ion-assisted platinum deposition. And we do that to protect the surface of interest while we're doing this sputter preparation. So the combination of the imaging capability as well as the cross-section capability in the FIB instrument allows us to navigate around on our sample. We can identify very small features, be they structures or defects, and then very precisely prepare cross sections of those for analysis. And we can adapt that to a transmission experiment through the following process. What I've shown here at the left side image is just a top-down view of a sample in which we've made two of these wedge-shaped cuts. We've left this very thin sliver of material between those two craters. And we have a micromanipulator contained within the vacuum of the FIB instrument that we can then bring down into contact with that sliver. We use the same platinum deposition process to weld that sliver to the end of the probe, and then we cut away any remaining material, lift that sliver containing our region of interest completely out of the sample. We then move that over to a sample support grid, which will allow us to introduce it into the microscope. Again, this is all completely contained within the FIB instrument. We again weld the sliver to the support grid with platinum, cut away the probe tip, and leave ourselves with a freestanding sliver of material for analysis. And then using the FIB beam, we very carefully thin that down to electron transparency. That's what you're seeing here on the right side. This particular sample is an optical coating that has an embedded defect, which you can clearly see here. And now we're ready to go ahead into our SEM instrument and do some analysis. So before I get into that, I'm just going to show here sort of a conventional SEM elemental mapping. This is a similar sample, optical coating with a thin embedded defect. This is a backscattered SEM image, reasonably high resolution, high magnification image. Again, in backscatter, materials that are heavier will show brighter contrast. And then if we go ahead and try to do our point-by-point EDS composition map, you can see we completely lose the resolution that we had in our SEM imaging. We can tell what the materials are here. We get a sense of what the layer structure is, but the interfaces are lost very quickly, and the degradation resolution is pretty obvious. If we switch now to this scanning methodology where we use a very thin sliver to confine the beam, the improvement is dramatic. So not the exact same defect, but the same materials. You can see we preserve the spatial resolution that our SEM offers us. The interfaces are very sharp. We can see layers here on the order of 250 nanometers to 50 nanometers in thickness. And so by eliminating that beam spread, our EDS analyses becomes much more resolved in terms of being able to show us what's going on compositionally in the sample. Just another quick example of that. This is a multi-layer film. It's actually a flake that's part of a light shifting ink formulation. And I just want to highlight the fact that we have these 20 nanometer-ish films on either side of the flake, and they're well resolved here in our subsequent transmission EDS map. You can see that they are chromium oxide. So again, by doing a transmission experiment and removing all the backside material really allows us to maintain the resolution offered by the SEM in our elemental analysis. What I'd like to turn to now is actual transmission electron microscopy, since we're dealing with thin samples. Now, rather than a scanning experiment, we're going to do a transmission microscopy analysis. This is the same diagram I showed you earlier, but now in the case of thin samples, we have the ability to directly transmit the beam through, and we have some other signals that we can use for analysis. So as I said before, while SEM offers very high resolution, there are some problems that require us to look at even higher resolving powers, higher magnification. A TEM uses a higher energy beam than is typically used in an SEM. Higher energy gives us a shorter wavelength, and shorter wavelength translates to higher spatial resolution. And again, rather than using electrons that are being emitted from the top surface, we're going to use the electrons that are transmitted directly through the sample to form our images. So in the transmission electron microscope, we have a set of electron lenses, and completely analogous to light microscopy, where you have light shining through a transparent sample through objective lenses and eyepieces so that the observer can see it in detail. These electron optics will maintain the spatial resolution of the transmitted electrons as they pass through the sample, which sits in this position here. And it will form a global image on a fluorescent viewing screen, which we can also capture using a digital image capture camera. The combination of these objective, intermediate, and projector lenses determines the magnification at which we view this image. But again, it's an instantaneous global image of the sample, not a raster scanned image as we form doing our conventional SEM microscopy. TEMs, as I said, operate at generally high incident electron energy, typically 200 kilovolts, as opposed to a SEM, which operate up to about 30 kilovolts, but we're usually use much lower energies when we're doing SEM imaging. And a TEM then will give you two basic modes of operation, which I've attempted to show here schematically. First off, obviously we want to do imaging, and those lens elements, as I mentioned before, act to create a magnified image on the viewing screen or the image capture camera. We can adjust the magnification of that image by changing the strengths of these lenses, and TEMs will typically offer magnifications up to 1,000,000x or greater. Also, if our sample contains crystalline materials, the crystal planes within those materials can act as a diffraction grating and produce Bragg diffraction of the electron beam. And by changing the strength of these lenses, then, rather than viewing this global image, we can cause that electron diffraction pattern to be imaged on our viewing screen or captured on our camera, so that we can begin to get crystallographic information from the sample as well. In our imaging, we have two basic modes, bright field being the most common, where we use this directly transmitted beam to form our image. We see image contrast in those images due to a combination of effects. There's a mass effect where elements or materials that are heavier within the field of view have a greater electron stopping power. They don't transmit electrons as efficiently, and they will appear darker in our image. Diffraction, if it's occurring in the sample, will also cause contrast in the image. Again, we can lose electrons due to diffraction. And if we use a small aperture in the beam, we can select those out, and materials and regions within the field of view that have some crystallinity to them will also appear somewhat darker than the rest of an amorphous region. Thickness can also play a role. Fortunately, the FIB instrument gives us nice parallel sections, so we don't have to worry about that too much. But in samples where there is a thickness variation, obviously a thinner portion of the sample will more efficiently transmit electrons than a thicker portion, and you'll see contrast due to that. We can also, rather than selecting out the diffracted beams, we can specifically select one or of them to use to form our image. And I've shown that here, where we take this aperture, and rather than selecting the directly transmitted beam, we center it over one of the diffraction spots in a diffraction pattern, and then use these electrons to form our image. And what that will do then is show you a distribution within that field of view of where the crystallites are that are contributing to that particular diffraction spot. As powerful as it is, there are some limitations to TEM. As with SEM, this is a vacuum technique, so samples need to be vacuum compatible. The sample preparation, as you've no doubt figured out already, is more time consuming than for the standard SEM type analysis. We're using high energy beams in relatively small areas, so beam damage can occur in some radiation sensitive materials. We do have some advantage here though in that we're not forming a raster scanned image, so we don't need to finely focus that beam down on a spot, and we can actually demagnify the incident beam to create a lower current density while still maintaining resolution in our transmission image. It's an ultra high resolution technique. We're typically working at high magnification, so we're looking at very small areas. Because of that, it's very good to have some prior knowledge about the sample. Certainly you're not going to use TEM for bulk characterization. You really want to have some previous information that allows you to hone in your TEM analysis on those features that it's necessary for. And finally, while the sample is very thin, it does have a finite thickness, and that entire volume is going to be seen in the resultant image. So a TEM image then is a 2D projection of this three-dimensional volume. A feature, for instance, that may be nearer to the top, the front surface of the thin sliver, will be superimposed on features that lie behind it deeper within that thin thickness. And you need to keep that in mind when we're looking at TEM images to avoid misinterpretation. So let's move now into some examples of TEM imaging. I've started here with just a metal on silicon microelectronic device, and I'm going to directly compare the TEM image to a SEM image. The SEM image on the left here is actually in a backscatter mode. So again, materials that are heavier will appear brighter in this image, and we can see several features immediately. We see oxide, we see this thin deposited layer. The oxide in this region appears to have two films, the bright material lying on top of the polysilicon gate material, as well as the contact here, which is tungsten. The same features show up in the TEM image, but there's some added detail as well, and the interfaces in general are somewhat sharper. Again, this is a relatively low magnification TEM image. It's just scaled to sort of provide the same magnification as our SEM. But you can see that the diffraction contrast is allowing us to see the polycrystalline nature of the poly gate. You can see the spacer material that's being used at this edge is very clearly defined, where it's a little tough to make out in the SEM image. Same with this interface boundary between the two dielectric materials. So a lot of information even in a low magnification TEM image relative to SEM. And I should point out that even though this is a somewhat low magnification image for a TEM, that the pixel resolution here is about 1 nanometer per pixel. And we're only going to go up from there in terms of magnification. And as an example of that, I've shown here a series of germanium and silicon lines that were grown epitaxially on single crystalline silicon. This is actually used as a magnification calibration standard for the TEM. The 5 dark lines you see here are germanium. Again, they're heavier, so they show with darker contrast than the surrounding silicon. And we can measure very precisely the various dimensions on these. These lines are on the order of 10 nanometers or so. If we increase our magnification, now we're just seeing 3 of these lines, but hopefully You can see also some fine detail beginning to emerge in the background of this image. There's some lines running roughly at an angle from left to right that you can see. And what we're seeing there is just the beginnings of being able to distinguish the actual lattice in this single crystal sample. And if we go up even higher in magnification, that's readily apparent. So now we're looking at the lattice planes in the sample. We can see that they run very continuously across the boundaries between the silicon and the germanium films, indicating that we do have true epitaxial growth. And in this case, we know that the silicon 100 lattice parameter is 0.314 nanometers, so we can use that as a fundamental yardstick to calibrate this image. And what I've done here is measured off 10 of those lattice spacings and assign that length on the image to what I know is 3.14 nanometers. And then I can go back and very accurately measure any other feature in this image. And in fact, that's what we do. We work back as we decrease the magnification and cross-correlate all these images so that in the end our full magnification range is calibrated to the silicon lattice spacing. So as we saw in the lattice image, we'd look to have complete epitaxial growth, and we can verify that using electron diffraction. And what I show here then is another image of this sample. The dark ring you see is the actual projection of an aperture that's been inserted into the beam to just select this portion of the field of view for diffraction analysis. There are a variety of aperture sizes, and combined with whatever magnification is necessary to see the field of view of interest, we can change the amount of material we include in our diffraction pattern. But if we take a diffraction pattern from this entire area, we get this very nice spot diffraction pattern indicating single crystal growth. And if we compare that to a published diffraction pattern from silicon, you can see that we have no extraneous spots. We truly do have single crystal epitaxial material. So the diffraction capability allows you to get crystallographic data from your sample as well as just imaging. Another example of lattice imaging, this are a couple of images from a graphitic carbon sample. Again, this is typically used to check resolution in a TEM. You can see the lattice fringes following around the particle contours, and the spacing in this case is 0.34 nanometers, 3.4 angstroms, so very high resolution capability in the imaging mode. So I'd like to step through a few examples. Again, now this is from the microelectronics. This is that same image I showed you earlier, and what we're going to do is look at higher magnification at the various features that are within this sample. Starting with the metal level, if we mag up on the metallization, we see the aluminum metallization. We're getting some diffraction contrast that highlights the presence of some smaller crystallites, as well as a larger, almost vertical grain boundary between two large crystals. We can see layers on either side of the aluminum also appear to have a polycrystalline structure, and again, since they're darker, are no doubt composed of heavier elements. If we mag up even further on one of those layers, in this case the underlayer, we can see that rather than a single layer, it's actually a bilayer, where we have a 22 nanometer initial layer deposited on top of the oxide, followed by a 28 nanometer top coat. The top layer is showing columnar grain structure. We also see some templating coming from the layer beneath it. So able to examine this particular region in very high magnification, and we can also do EDX work on that, which I've shown it with this inset. The film below the aluminum then is identified as a titanium nitride. We see some aluminum from the metallization as well as silicon and oxygen from the dielectric. And we also see some extraneous peaks in the spectrum. Gallium is due to the use of gallium in our fib beam. We also see some copper, and it's possible that there's copper in the sample, but more likely that this is copper coming from the use of a copper grid as the sample support grid. Remember back when I showed you the fib sample prep, we had the sliver attached to a grid, and these are typically copper. If copper is of particular concern in analysis, then we would not want to use that, and there are alternative grid materials that can be used in that case. Molybdenum is very frequently used if there's a need to know for sure whether copper is present in the sample. If we look now at the polysilicon gate material, again, we have this dark material that's on the top. Point spectra EDX shows that to be cobalt silicide. Again, we see this small copper peak, which lends credence to that just coming from our copper support grid. You see the polycrystalline nature of the silicon here that's in the gate, and single crystal silicon beneath it obviously doesn't show that. And we have this thin layer between the two, which is the gate oxide used in this MOS transistor. And we can look at that in even higher detail. This now is a high mag image, ultra high magnification, to look at the gate oxide and check its dimension. Once again, we see lattice structure within the single crystal silicon substrate, and also in areas of the polycrystalline silicon above it. Although again, since this is poly, we have different crystal orientations, so we get a mix of different lattice directions. But since we have this nice lattice on each side of the gate oxide, we can make a very precise measurement of its thickness, in this case 2.6 nanometers. So very high resolution imaging capability. And a very accurate measurement, since again, we can refer that back to the silicon lattice, the known lattice spacing. So from that example, you can see that TEM is an extremely powerful tool for interface characterization. This slide just shows a quick example where we have two contacts, again, in a microelectronic devices, one of which shows good electrical performance, the other of which showed high resistance. And you can see in the high resistance contact, we have this additional bright layer that we don't see in the passing contact. Again, if we go and get EDS compositional analysis in this area, we see a fluorocarbon species, which could be due to an etch residue, what has given a high contact resistance in this instance. Just another example of interface characterization. This is a sample that's an optical coating, again on a semiconductor substrate. When we had done some initial work on this in the SEM, it looked like there may be some possible delamination at the bottom interface between our coatings and the substrate. And so we then went ahead with a TEM analysis to look at that in greater detail. And what you see here is that we do not see delamination. Again, delamination being a hole where we have missing material, would it be expected to show bright in this bright field image? And instead what we see is a darker region that looks to be just a change in morphology as we move from the initial stages of the depth into this more polycrystalline, larger crystal size material above it. Just continuing with the thin film characterization. This particular sample is a metal thin film coating on a molded polymer substrate. Again, I've shown a SEM image. In this case, a very high magnification, good quality SEM image. We've rotated it by 90 degrees to move it away from the scan direction of the raster scanned image that tends to show these interfaces a little more clearly. And what you can see in the SEM is that we do see a layered structure. It's about 55 nanometers in thickness, but that's about all we can tell from that. If we go into the TEM, then we obviously see these layers in higher magnification. We can start to pick up some diffraction contrast that indicates crystallinity within the metal subfilms, as well as this boundary film. One thing to point out, again, coming back to the fact that this is a three-dimensional projection, a 2D projection of a 3D volume, is that unlike our gate oxide case where we had sharp interfaces on either side, we have some surface roughness in this case, particularly as we move up the stack. And what happens there then is you can think of the individual roughnesses within the planes all superimposing on one another, and that tends to smear out the interface in this projected image. So we could try to clarify that somewhat by moving to an even thinner sample. Obviously, you're playing the game of getting the sample thin enough without losing it completely. But still, a lot of additional detail in the TEM image. Again, this is a polymer substrate. We can do polymer materials in the TEM. We do have to be careful in terms of irradiation damage, but many polymer materials are suitable for TEM analysis. And again, we can do our EDX work to look at compositions. In this case, we see a tie adhesion layer followed by layers of stainless steel. Again, we're picking up this copper peak, which is from our copper support grid. So again, very important that if copper is of interest, that we know that ahead of time so we can select an alternative material. Just continuing on here, both interfaces are a technique or an area that the technique is amenable to. Thin or small defects is another one that TEM really shines in. This again is a multi-layer optical coating that was showing poor performance. Our cross-sectional SEM showed defects, buried defects in this material down here at the first layer. However, from the SEM imaging alone, it was difficult to tell if those defects had been deposited on top of the layer subsequent to its deposition, or deposited with it, or perhaps were present before that layer went down. And so by moving on to a TEM analysis, we're able to look at that defect with much higher resolution, and we can see that it extends all the way down through the film. Hopefully you can make out the edges of that defect where I've positioned my cursor. Again, we have this projection effect going on here. This is only a 50-ish nanometer particle. Again, the sample thickness is on the order of 10 times that. So you have areas where this initial film has been undisturbed that are superimposed on the particle itself, and which is why you see what appears to be that layer running unadulterated right across the particle. Transitioning now to another type of sample. This is a nanoparticle example. Nanoparticles find application in a variety of important technologies. Catalysts being one of them, also composites or energy storage systems. What I have here is this nanoparticle cluster, and in this case, the sample is thin enough out of the box, if you will, that we don't need to do any additional thinning, right? This not required to thin this any further. You can see we have particle sizes here on the order of 20 nanometers or less. So that's already small enough to be electron transparent. So they could be deposited directly on a TEM support grid, which has been coated with a very thin organic support film and imaged directly in the TEM. And again, this image shows a variety of particle sizes. We see some diffraction contrast appearing here, which would indicate crystallinity. And we can again use our diffraction analysis to confirm that. So if we select this region, this cluster for diffraction analysis, we get this diffraction pattern. And this dark line that you see running through it is just a physical probe that's inserted in front of the camera to avoid burning out the image capture camera with the directly transmitted beam. So you see diffraction spots that are forming this ring shape. Again, that's due to the random orientation of the crystallites present in this cluster to our incoming electron beam, and they scatter and give diffraction spots along the radius of these various circles. If we had even more material in this region, we would have even more orientations, and these would fill in into ring patterns, much as you get in a powder diffraction pattern. So wrapping up here, so advantages of the TEM. Hopefully I've shown you that it does provide an ultra high resolution imaging capability. In addition to that, we can get some information on crystallinity and the crystal structure itself. It's a thin sample by definition, and we are using a high energy electron beam. So we get very little spread within the sample, and we can provide high spatial resolution EDX work. And one thing I may not have pointed out specifically up to now is that many SEM samples, and particularly those which have been fibbed prep for the SEM work, can be converted to TEM samples if we see something in that initial SEM analysis that we'd like to examine in greater detail. So in summary, a high resolution imaging and microanalysis capability. It's applicable to a wide range of materials. I've shown you some examples from microelectronics, thin films, coatings, nanostructures, small defects, and interface characterization is a real strength of the technique. And not to lose sight of the fact that sample preparation is a key component in the analysis. You need a high quality sample prep to achieve a high quality TEM result. And with that, I'd like to open it to questions. While we're doing that, I'll also flash up that we have a couple of upcoming webinars. Next month is a webinar on the analysis of polymer and composite failures. In December, as Christina mentioned, we had a client submitted topic, analytical solutions to your engineering and manufacturing problems, aka which tool works best to solve which problem. So again, I'm going to open the floor to questions. If you have specific questions that you'd like, we can answer those offline also if you email to answers@analyticalanswersinc.com. So the first question I have is, how large a field of view can you prepare for TEM? So while we cannot image the entire field of view at once, we typically prepare sections that are about 10 microns in length of electron transparent. We prefer to do smaller than that, just to maintain mechanical stability, but that's kind of the limit of where we are with the fib preparation. Second question I've received is, can any material be prepared for TEM? Most likely not. There are some restrictions around what we can put into the transmission electron microscope. Again, the most important being that it needs to be vacuum compatible. It needs to be able to stand up to the fib preparation. If we go the fib route, there are many materials that can be used for TEM, however. So if you have a question regarding whether it's suitable or not, certainly get in touch with us and we can let you know. Can TEM be used to measure crystallinity index as XRD? Well, as I showed you, we can have the, in a single crystal sample, we get the well-resolved diffraction pattern that we can use to measure lattice parameters and that sort of thing. Another question here, is EDS analysis in the TEM or STEM more time-consuming than in the SEM? And the answer to that question is no. It typically takes about the same amount of time once you have your sample in the instrument to actually generate the EDS analysis. Can you do grain boundary imaging and analysis in the TEM? Typically the answer to that question is yes. Again, it can be somewhat sample dependent, so if you have a problem along those lines, again, I would certainly encourage you to get in touch with us and we can see about designing an analysis to address that. Can you do grain or particle size analyses from TEM images? Again, the answer to that in general is yes. Can you make a TEM sample from a 4-inch wafer? Yes. Again, though, it's a lift out sample, right? So, but on a 4-inch wafer, if there are small structures or small defects that we need to find, the capability exists to drive to those positions and then excise those regions of interest from the wafer and prepare them for subsequent TEM analysis. Any additional questions at this point? If not, again, I would encourage you to submit any questions you might have either via email or give us a call here at Analytical Answers. Oh, here's another question. What is the difference between high resolution TEM and STEM? So STEM in its name implies that you are scanning the beam, right? Scanning transmission electron microscopy. And so in that technique, we would form a finely focused probe beam, step it across the sample in a raster fashion to generate the image, much as is done in an SEM. In a high resolution TEM image, or TEM in general, it's not a scanned mechanism, right? We rely on the electron optics to form a global image of the sample, much as you would in a light microscope. Okay, well, if there are no further questions, I think this ends the technical portion of the webinar, and I'll turn it back over to Christina.
Okay, well, this is Ed Norton, Technical Director here at Analytical Answers. I guess we're not able to get Christina back at the end here, but I would like to say thank you to everyone for coming. We look forward to seeing you in November and December, especially in December because that was a customer suggested topic and we think it's going to be a very good one. So we look forward to seeing you for the rest of the webinars for the year, and I hope everybody has a wonderful day. Thank you.